I'm Dr. Julie Whitney, and in this second video, we're going to be talking about signal to noise.
While signals are the things we use to transmit information, noise is what the real world throws at us to get in the way. Most of us are familiar with noise as being the background sound waves that get in the way of the thing you want to hear, your music, or someone talking to you on the phone. Noise has a broader meaning as well. It's any unwanted energy that is superimposed on your signal. Think of it as the static on a radio station, or the bounciness in your data. The switching of the direction of the electricity in the walls frequently puts a 60 Hz noise on poorly designed electronics. Solar flares can create electromagnetic storms that disrupt power grids and communications. And light can even create noise if it interacts poorly with lenses. We measure this quality of information in something called the signal-to-noise ratio. The signal-to-noise ratio is a comparison of the amplitude of the signal you want compared to the amplitude of the noise that you didn't want. And in this case, the signal was this slowly decreasing line, and the noise was this bounciness. And what we see is this jaggedy, slowly decreasing signal. Why does it matter? Well, we want to get information out of our signal. And the more the signal and the noise look alike, the more difficult that is. So we want a high signal-to-noise ratio. The easiest solution to get there is to have a signal that's much, much bigger than the noise, so you can ignore the small variations going on in the background. But what if your signal-to-noise ratio isn't as good as you like? Well, then as an engineer, you should go back and look at what you can do about it. You may be able to tighten up or make more repeatable your mechanical setup. You may be able to shield your electronics or sample your sensors better. You want to make sure that your physical design is as good as it can be. But let's say it is as good as it can be. What else can you do? Well, one strategy is to take an average. An average allows you to look at data and find the underlying slow trends. This data is from a water sampling or water level inside a mine. The water sampling is taken by a float that sits on top of the water, and so of course as waves come through, the float goes up and down. But the overall trend of the float going up and down is the water level you're trying to measure. And so if you take a running average, you can get rid of that little bounciness that are the waves and concentrate on the underlying signal, which is the level of the water in the mine, which is what you want. Filtering is strategy 2. Filtering can take advantage of the fact that your noise is frequently a different physical phenomenon, a different physical cause than the signal you're trying to do. In the image here, the noise is the light bouncing off of the water. And because that's the noise, we know that it's coming at us at a given angle, kind of low to the horizontal. So a polarizing filter can be used to remove that information. There's another kind of filter too, and that would be a frequency filter, very, very commonly used on electronics. Let's say your signal looks like this top one here. It's very bouncy and has sort of this oscillation in it. If we take a mathematical transformation called a Fourier transform and look at it again, what we do is we plot, instead of time, we plot frequency. And we can see which frequencies are the dominant ones in our signal. Now let's say that the low frequency is the one you really want. The higher frequency stuff, like the bouncing of the float, is just noise. Well, I can use a low pass filter. That will allow just the low frequencies to go through, and the higher frequencies get have the volume turned down on them. They're not totally gone, but they are not as prominent. Similarly, if I really like the high frequencies and that low frequency isn't something I want, I can use a high pass filter. And if I want something in the middle, I can combine the two filters for a band pass filter. Frequency analysis can help you debug problems. This image has a defect called banding in it, and we dealt with this a lot at Lexmark. Now the banding happens periodically, and by understanding the frequency of that, I can go back and look at all the mechanical components going round and round in the system and find the one whose diameter matches the frequency of this defect. Then I'll know where to look to start solving the problem. So tools for getting a better signal-to-noise ratio, number 1 is increase the signal, and number 2, decrease the noise. If that fails, or maybe in addition, you can average the signal to get rid of small jumpiness, or you can filter the data based on the physics of the noise, its frequency, its angle, its intensity, something like that.